Okay, so today we're going to look at two powerful approximation techniques, often used in applied mathematics, when a function is just too complicated and messy to work with. Okay, we can use a simpler function. So imagine the biggest, baddest, ugliest function you can think of, just a giant mess, right? Ugh, right, I do not want to deal with that. I do not want to have to plug things into that function. It's just awful, right? So maybe I could just use a simpler function that has similar behavior to my nemesis function, right? And it actually is completely possible to come up with a function that's much simpler but has similar behavior, at least on a local scale, right? At least in like some small region, you can create a function that looks just like your really ugly function, but is much, much simpler. Okay. So in general, in this class, what's the simplest kind of function we typically work with? A line, yeah. Well, yes, the identity function y equals x, but a little bit more general than that, a linear function. Right, linear is typically the simplest function that we work with in this class. We build this simpler linear function using calculus. Okay? We want it to have the same behavior as our big bad function. So we make sure that it has the exact same value at some single point. At one point, we want our line and our big bad function to have the same value. Okay? So we make sure that they match at a single x value. We'll call it x equals a. And then we also make the derivative of our big bad function and the derivative of our simpler linear function also match at x equals a. Okay? And that's it. We call this thing the linear approximation or the local linearization of the function at x equals a. So here's our ugly function, right? The square root of 1 plus x. And I know this one is not too bad, but before calculators, it was a really big pain, and we're going to use it to demonstrate the method before we start using really, really ugly functions. So I want to build a linear function that behaves similarly to f of x, radical 1 plus x, near x equals 0. So I'm going to have my f of x function, which is radical 1 plus x. And I'm going to have another function, my line. I'm going to call it L of x for my linear approximation function. And it's going to be a line, so it's going to have a form like ax plus b. And I'm going to use a instead of m. You'll see why when you get into the group activities. So a is just representing slope. All right, so I need my two functions to have the exact same value at 0, right? If I'm trying to approximate f of x with L of x near 0, let's make sure they are exactly the same at 0. Okay, so I need f of 0 to equal L of 0. So what is f of 0? 1. And what is L of 0? B. Okay, we now know what the y-intercept of our linear approximation has to be. And then I also need to make sure that f prime of 0 equals L prime of 0. Okay, so these are my two pieces of information that I must make sure match. The function and my line have to be the same at 0, and their derivatives have to be the same at 0. Okay, so let's take the derivative of f prime of x here. What's the derivative of f? Yes, close. 1/2. 1 plus x to the negative 1/2, and then you threw that in the denominator, 1 over 2 square roots of 1 plus x. All right, so what is f prime of 0 then? 1/2. Okay, what's L prime of x? What's the derivative of ax plus b? A. So what is L prime of 0? Say it louder. A. This is a constant function. No matter what the input is, the output is A, right? So L prime of 0 is A. So I now know my slope of my linear approximation function. So L of x is 1/2 x plus 1. We call that thing the linear approximation. It's got the same value at 0, and it's got the same derivative value at 0. All right, I'm going to let you work through the rest to uncover all the details about why this works, why this is a good approximation, and that also will lead you through a quadratic approximation.